Okay, guys, so today I just want you guys to take a look at this worksheet called the Gas Laws Worksheet. So we've been talking, or just you guys have been exploring the gas laws, which is the idea that, like, if you have a gas and you heat it up, it's going to expand. If you cool it down, it's going to contract. Um, the idea of pressure, that there's a lot of gas inside of a container, there's a lot of pressure, and then on the outside there's air pressure pressuring in. And so there are these different relationships between pressure and volume, and they're captured in these three formulas. These are the so-called gas laws. So there's the Boyle's law, which looks at the relationship between pressure and volume, Charles's law, and the Gay-Lussac's law. And these are the actual three scientists that the lessons are known for. I mean, that the formulas are known for. So, just using your own intuition and based on what you know, just answer the first three questions. If a balloon is moved from low temperature to high temperature, do you think it'll expand or contract? If a balloon is allowed to float from ground level, where the pressure is very high, way up into the atmosphere, where there's almost no pressure, do you think that the balloon is going to expand or to contract? And then think about, say, like a can of metal, like a metal can, and you heat it up and then you put it on ice. Like that was that demo we looked at last week. All right. So, conceptually, whether things are going to expand or contract, pressure is going to go up or down, volume is going to change. But now just let's just do it quantitatively. Okay. Let's just look at the formulas. And so I'm just going to walk you through how to do this, where you actually are just going to use the numbers and just calculate the actual answers. So, for example, here, problem 4. Just read the problem. You are flying in a commercial jet where the sealed cabin is 1 atmosphere. Atmosphere is just a measure of pressure. That's sort of normal air pressure like you would have on an airplane. Suddenly, though, there is a loss of cabin pressure and the pressure drops to zero point 0.7 atmospheres. So the pressure got less. So you may have ever had this experience with your ears. In your middle ear, it may feel pain in your ear if you go through changes in pressure, like on an elevator or in an airplane. So if your middle ear is normally 0.02 liters, okay, that's the volume of the air in your middle ear. What size does your middle ear change to if the pressure drops? So if the pressure drops, the air in your middle ear is going to expand. It's going to be painful. All right. But anyway, just calculate it. And just all you have to do is go P1. So P1 is 1. So that's 1 atmosphere. All right. And that's going to be times volume 1. So the volume normally here, V1 is 0.02. 0.02. Okay. And that's going to equal the new pressure, P2. Okay, so that pressure dropped to 0.7 atmospheres, 0.7. Okay, and what you don't know is what size does the middle ear change to? What's the new volume? So what you don't know is V, okay, or times V. You don't have to put the times, the multiplication symbol in, right? And all you have to do then is just do the algebra here and then solve for V. All right, pretty basic. Okay, question 5 says a balloon with volume V1 equals 4 liters and at pressure, say a little higher pressure, 2 atmospheres, is taken up in an airplane where the pressure becomes less. So if you go high up in the atmosphere, the pressure is less. What's the new volume? Okay, so now you're using um, the same formula again. You're going to put in P1. P1 is 2 atmospheres, and that's going to be times the first volume, which is 4 liters. Okay, and that's going to equal, now we have the new pressure is 0.2. Okay, and then some new volume, right? So probably that volume is going to be higher on account of the fact that the air pressure is less, right? So a balloon, as it goes up in the air, is going to expand. All righty, and then you can move down to question 6. Um, let's say, have you ever used a pressure cooker at home? The starting pressure, let's say, is 2 atmospheres, and then it has a starting temperature of 300 degrees Kelvin. Um, and now you heat the pressure cooker up, so you turn it on and it gets hotter, right? And then it becomes a higher temperature. So what do you think is going to happen to the pressure on the inside? Well, if you heat up the pressure cooker, right, on the inside, the pressure is going to be higher, right? But in any case, let's calculate it specifically. All right, so P1 is 2 atmospheres. So you just have 2. It's going to be divided by the initial temperature, T1, which is 300. All righty. And then the initial, so you don't know what the secondary pressure is like after you've heated it up, okay? But you do know what the temperature is, and it's 600. Okay, so again, I'll leave it to you guys to do the algebra to go ahead and solve for the resulting pressure. Now, question 7. Again, let's try the hot air balloon problem, but this time without respect to pressure, let's think about temperature. You release a hot air balloon. The starting temperature is 350 degrees Kelvin, okay, and the starting volume is 100 liters. When the temperature reaches 400 degrees Kelvin, what's the volume? Okay, so this is another one. T1, V1, T2, and you don't know V2. So you're basically just plugging it in, plugging in the numbers. V1, 100, okay, is going to be divided by T1, which is 350, and that's going to equal um, here. Well, we don't know what V2 is, so we'll just leave V, okay, blank, V, and that's going to be divided by the second temperature, which is 400. Okay, and again, I'm going to leave it to you guys to go ahead and solve, do the algebra. Alrighty, so these gas laws named after these 3 scientists, and they can look at 2 at a time: pressure, changes in volume and temperature, changes in pressure and temperature, which I think you know conceptually, um, but this allows you to be a little quantitative. So take a crack at it, go ahead and try this assignment, and we'll see how it goes. Thanks a lot, guys. Hope you're staying safe.